All right. Hello, my name is Odessa Rybski, and this is the culmination of a couple months of work on Windows malware and sandbox detection, how malware detects if you're in a sandbox. Starting off, who am I? I'm Odessa, she, her, third year cyber. I run Void, Linux, Windows, and Ubuntu WSL. Don't run Void. Wannabe malware researcher. I just do this for fun. Enjoyer of strange and unsettling music. I go to a lot of raves, go to a lot of shows. It's a lot of fun. Body modder with a low pain tolerance. Don't ask me how that works, because it doesn't. And there's some pictures of me. Before we get into this, disclaimer, I am not a professional. This is all my own research. Some of it might be a little wrong. Some of the things I found might be a little weird. I don't get paid to do this. This is solely my own work. Presentation focuses mainly on Windows malware and Windows sandbox detection techniques. This is due to just what I've researched. I don't have enough experience in Linux malware and how Linux sandboxes work to really make a statement on that. Some of these techniques may work the same. They may not. I don't know. If you want to dive deeper into this after the presentation, feel free. It's a lot of fun, and don't use any information in here for evil, please. Starting off, what the hell is a sandbox? And within that, what is a virtual machine? So a sandbox, virtual machine, I'm going to be using those terms pretty much interchangeably here. A virtual machine, if you've learned about, I don't even know what you learn in 140 anymore, but it's a guest OS inside of your own operating system. Every virtual machine has parts of the host, CPU, RAM, and storage allocated specifically to it. The OS, the guest OS, the VM, lives on top of what's called a hypervisor. The hypervisor is a piece of software that interacts with your kernel or with your kernel through an OS. That's a type 2. And the hypervisor handles how the VM gets created, how stuff gets allocated, and certain more complicated things, which we'll get into later. There are two types of hypervisors here. Type 2, which is where the hypervisor lives on top of your operating system. These are your virtual machine managers like QEMU, VirtualBox, VMware, Parallels on Mac, and Proxmox is actually a type 2. And then you have your type 1, where there is no operating system between the hypervisor and the kernel, and the most popular ones are KVM and Microsoft Hyper-V. Overall, virtual machines, just really useful tools in our field. If you need a certain setup that needs to be reproducible, or you're going to do silly things on it, like infect it. So what is a sandbox? In this case, it is a virtual machine that exists specifically to contain something. Hopefully, it's inescapable. It should be inescapable. In our field, mainly used for testing out malware, whether you're a researcher or you're a malware author. There are some popular online sandboxes where you can test run malware or any files, really, any exes. AnyRun is one of the most popular ones. FileScan.io and Joe Sandbox are two alternatives that I've used occasionally. For self-hosted, you have some images that you can get for free. FlareVM is probably the most popular Windows sandbox that exists. Don't know, at least in my 202, we used a FlareVM. Pretty sure we used a FlareVM, I don't remember. Another one is Black Arch Linux. It's sort of like Kali, but with more analysis tools and Arch. It's just silly. And then there's Remnux, which is a Linux distribution specifically made for reverse engineering. And then, of course, there's the option, just make your own sandbox. Just secure your own VM. Why? Why does this all matter? Sandboxes are really important for testing because oftentimes when you'll get a malware sample, you want to know what it does, especially if it's never been seen before. You don't really want to test that on bare metal because if you mess up, then your host machine's infected, and you can't exactly burn that and start fresh. But on the other side, malware authors will be aware that when their samples get collected, they'll be tested. And they don't really want you looking at their malware. They don't like that, because as soon as people figure out what the malware does, implementations can be put in place to stop it, which is bad for business. So malware authors will add in certain obfuscation techniques, popular obfuscation techniques, checking for a debugger, adding in garbage code that doesn't do anything to make the reversal process harder, encrypted functions that get decrypted at runtime, just bad code in general. Playing with multiple languages, that's one I've encountered a lot, and just weird jump calls. And because of this, Sandbox malware authors and malware researchers are sort of in an arms race for who can outdo each other. So moving on to simple techniques that malware uses to avoid being, or malware uses to detect that it's in a virtual machine. Malware wants to do this so it doesn't run in the virtual machine, and the easiest way to do this is normally just with software, just like regular C code. You can check things like the computer's UUID, usernames, host names, certain running processes that malware authors will know they don't want their malware run with. Certain malware strains also check network information, because AnyRun and Joe Sandbox specifically have known IPs. And so, oh, am I being run in here? Don't run. Another very good way to avoid detection is just like wait a couple hours before running. If you're a malware researcher, double click the exe, nothing happens, a little hard to see what's actually going on if it's going to wait a couple hours before anything actually runs, or days. That is a very passive way, but has been seen a lot in the wild. And lastly, just checking anything where there could be known strings that are unique to VMs. For instance, known registry keys for VirtualBox and VMware, if they exist on whatever host the malware is being run on. Those registry keys don't normally exist on actual hosts that you want to infect, and so it's a big red flag there. An example of some other stuff, I saw a Word document worm that would check if there are recent Word docs opened. Because why would you have a bunch of Word history in your sandbox, right? So if there wasn't any history, it just wouldn't run. It's a little, like, it's very simple, but you wouldn't really think about that. So for our simple VM detection methods, we can start with Umbral Stealer. It's a free open source stealer for Windows intended solely for educational purposes. This is, of course, why Malware Bazaar has 72 reports of it in the wild. It grabs all your default info stealer things, all the browser cookies, your tokens, crypto wallets, Minecraft worlds for some reason. It's open source, so you can just go read it. Like, you can go see exactly what it does. Then, of course, like your computer info, screenshots, and webcam photos. It has basic AV blocking. It isn't the greatest. Again, it's a free open source stealer. It's not the most complicated. And it has basic anti-VM that includes obfuscated code when it's compiled. And if it detects a VM, it will self-destruct. It won't run. Yeah, here are some videos that just pop up when you search Umbral Stealer on DuckDuckGo. You know, in case you want to use it or research it. Don't use it. So to look at some of the code, for its anti-VM, it has essentially a bunch of hard-coded blacklists, specific UUIDs, usernames, host names, processes, providers, and then, of course, a debugger check. You can see right in the middle there, blacklisted users. Some of these are very specific. Of course, this is editable. You can add your own users, but some of these, like known default machines that you don't want running your code, or known malware researchers that you don't want playing with your code. This, however, is all on the software level. They're nothing deeper than that. Other examples of software checks, Win32 Zeus, that strain and family of malware, checks for VMware and VBox strings and registry keys. SIMDA checks product IDs of the virtual devices for known Sandbox services. If you don't change those, they'll be certain range by default. You don't want that. Illyrian uses WMI queries to check more information about the virtualized hardware, but it doesn't actually go deeper than that. This is still technically a software detection. Now moving on to the more complex stuff. So this is where how VMs work gets a little more important, because we're no longer so focused on detecting the operating system itself. We're more focused on detecting how the VM operating system interacts with the rest of the world, and specifically the hypervisor. This is because on bare metal, you don't have this hypervisor, so any behavior that is caused by the hypervisor is a lot harder to remove, a lot harder to mask. And on the same hand, if you know what you're doing, easy enough to detect. Some of these hardware interactions are checking your drivers, or like doing things with drivers, device drivers, also how VM escapes work a lot of the time. But because of that, because this hypervisor gets involved and works with drivers, works with these physical layer devices, behavior can start to get unusual. So starting off with some simple stuff, checking power and sleep modes. For thermal, you can check thermal control on your VM. You wouldn't really think about that, but since the virtual machine doesn't have any physical components that it knows about, it could be misconfigured by default. Some things could be missing. There could be very generic information, again, known strings that you can check. Same with sleep modes, but virtual machines are also a little different with sleep modes, especially in Windows, where you can't access certain sleep modes because it's virtualized. And so it's not always 100%, but it's worth raising a red flag over. And now we get into the really fun stuff. RDTSC, read timestamp counter. This is a little call that just reads the current CPU timestamp, the clock cycles. Just gets a little time. More importantly though, it runs really fast. It's an assembly call, so it interfaces directly with the hardware. All it does is it takes a little bit, it just gets the time. But when used correctly, used one after another, you can measure the time between 2 points. So if you use something that causes hypervisor interference between two RDTSC calls, that might look different when there actually is a hypervisor versus when you're just talking to bare metal. Yes?
What's an example of one of those syscalls that would take longer because of the hypervisor?
Getting into this right now, actually. Yeah. So I'll start with that. Some of these calls, CPU ID, getsec, INVD, xsetbv, invept. You can read. I don't know what most of them do. I focus mostly on CPU ID. Yeah, starting at the top. Because all the hardware is virtualized, things can get weird. In a virtual machine, you have root level operations and non-root level operations. This is because when you create a VM, you still have allocated hardware. Like, you're still using the hardware there. But you really don't want some calls to directly interact with the hardware, because that's where what you do in the VM starts to escape, and once you're messing around with like I/O and very low-level things in a VM, you can start directly influencing the computer. So what hypervisors do is they'll have a list of certain calls that they trap. It's called a trap and emulate, where certain functions get trapped, controlled, and then sent to the hypervisor to be handled. And yeah, those are the examples up there. These are specifically, they all cause a VM exit. So a VM exit is when a call gets escalated to the hypervisor, or something gets escalated to the hypervisor. All of these calls exit regardless of whatever you do. So, like, you can't change that. The function gets trapped. Hypervisor then emulates said response, again, because we don't want directly talking to the host machine. Going on to specifically CPU ID, the AMD docs are better if you want to read up on this. The Intel docs are awful, but you know, you do what you got to do. CPU ID by itself, all it does is gets information you want to know about the CPU. It's a rather benign call, but we're not using it for that. We're using it because in a virtual machine, when you use CPU ID, that automatically gets sent into the hypervisor to be handled. You can see the top diagram there is basically what happens. It gets called, answer gets emulated in the hypervisor, a VM resume is called, and then gets sent back. Now compare this to bare metal where it just runs. You call CPU ID and it gets the information back, just like that. Going back, RDTSC, remember that? If we get timestamps before and after, on bare metal, the time will be much smaller than in a hypervisor, to the point like where like CPU speed is not going to be the cause of a red flag here. The hypervisor just adds so much extra time for this that it'll be noticeable. So yeah, if a malware that uses this detection gets this red flag, sometimes it'll change its behavior, or sometimes it'll exit completely. How do we use this defensively? Yeah, so paranoid fish. This is what we're going to use to test everything we try. PA fish, testing tool that uses different techniques to detect virtual machines in a malware analysis environment in the same way that malware families do. It runs all the checks without any malicious behavior. It's pretty well, it works pretty well. It's a good benchmark. I haven't used Open Canary as an alternative. Alkazer is a lot more in depth, but you don't need that most of the time. PAFish, it's literally just a script you run. It's very simple. So, bypassing PAFish with simple detection, or for all the simple detection methods. Changing your hostname, making it seem realistic. There are several projects that exist to hide known traces of hypervisors, so known registry keys that hypervisors will set. You can, I believe it was a rootkit I ran of some kind that I got off of GitHub that I ran on this Windows VM, and it changed them around enough where it didn't need to do that. In the virtual machine file, you can change the names of your physical drives, what they're labeled. So in this machine, I have an Intel CPU and a 10-cent SSD. That's a Chinese brand. This is an anti-VM that I made early summer, and this was in VMware, so I wasn't able to get the bypass for RDTSC working. So that's the only flag that's raised. You can see there in the bottom corner. That's all PAFish detected. Going back, there's a lot of detections, and so I only got one trace. Moving on to how do we get past RDTSC? How do we get past this seemingly unbypassable timestamp check? We can't force these specific calls to not be sent to the hypervisor. So instead what we do, we also trap RDTSC, you know? If we need to be editing things, why not just send the time check through the hypervisor as well? And when the time check gets sent into the hypervisor, it edits the time using a specific offset, sends it back, and then, so essentially it makes it look like the second RDTC call, when it gets sent back, will make it look like there was no hypervisor interference. Now, this isn't infallible. RDTSC is not the only clock that you can use to run this check. It's just the most popular one. You can do this with the other clocks, but again, it's Windows. It's going to be a game of cat and mouse. Windows APIs are, there's so many that have not been researched enough. It will forever be this game of cat and mouse. But normally, patching RDTSC in your KVM is, it's the most popular method. I think it's the only method. KVM specifically is the only hypervisor that this has been written for. It's open source, so it's a lot easier to work with. And also, there's such a small community of people that are doing this that like no one's gonna be writing a patch for VMware anytime soon for this. I would love to give a demo, but again, because there's such a small community, my AMD laptop does not work with current Linux version. The current Linux kernel with AMD processor, there isn't a project written for that. Also decided that doing like patching it last night when I still need my laptop for, you know, the rest of my life is probably not the smartest idea. So yeah, thank you. Also shout out Sharad Khanna for letting me ramble to him many late nights about this and keeping me going when burnout was right there. So yeah, thank you. Any questions? Yes, Stella? How can this be used offensively? Which part? You just want to write malware? Learn how VM escapes work. Learn how you can privesc to root from inside a VM. Yeah, Hayden.
Or like, you know, as you described, like anti-VMs, like is that something that researchers like actually use to try and?
Okay, yeah, the question was these anti-VMs, these invisible sandboxes, are these actually used by malware researchers? Yes. Yes, they are. This is how I was able to do my previous work on Luma Stealer. Wasn't perfect, but I was able to get a lot further with this invisible sandbox than I would have with a default sandbox. Yeah. Any other questions? Yes. Okay, so the question was, why deal with VMs at all? Why not just why not just get a bunch of like Raspberry Pis? And to that, I say, you have fun running Windows on a Raspberry Pi, and then we'll talk. Because I'm not. I already don't like running Windows in general. Yeah, any other questions? All right, should be it. Thank you.